Out of all the bizarre features of the universe that we talk about on our show, from black holes to quantum mechanics to exoplanets, it's easy to take for granted what's right in our backyard. Today we pay tribute to the most important astrophysical object in the universe. At least it is for us here on Earth. And maybe after this, you'll look up in the sky and think a bit differently about what it is that has fueled all life on Earth, our sun. If you're enjoying the discussions we have on our show, then there's another University of Chicago podcast network show that you should check out. It's called the Chicago Booth Review Podcast. What's the best way to deliver negative feedback? How can you use AI to improve your business strategy? And why is achieving a soft landing so hard? The Chicago Booth Review Podcast addresses the big questions in business, policy, and markets with insights from the world's leading academic researchers. It's groundbreaking research in a clear and straightforward way. Find the Chicago Booth Review Podcast wherever you get your podcasts. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. When we look up at the sky, one object stands out more than any other, namely our sun. Throughout most of human history, the sun was treated as an entirely unique and distinctive object, unlike anything else that we could see or know about. In many cultures, the sun was associated with specific gods in their pantheons and otherwise inspired a great sense of awe and wonder.
And you can understand why if you look up at the sky and there's this powerful beam of light that you can't even look directly at.
Yeah.
And it's somehow powering all of the plants and animals and life around you, and you have no context.
There's a giant magical ball of fire in the sky. How do you not get awed and like overwhelmed with mystery from that? Of course. Yeah. I'm not saying anybody was like being foolish by jumping to that conclusion.
No, for sure not. Something's up with that one, for sure.
Today, we view the sun pretty differently. It's we don't think it is a particularly unique object anymore. It's just one of the many, many stars in the sky. It's just the star that we happen to be up close and in close proximity to. We know that there are about 100 million stars in our Milky Way galaxy, and the Milky Way galaxy is only one out of about 1 trillion or so galaxies in the observable universe. So there are lots and lots of stars. But of course, the sun still, it impacts us more than any other star just by virtue of it being in our cosmic backyard, if you will. So the first person, or at least the first person that we know of, to argue that the stars in the night sky were objects at least similar to the sun, but just farther away, was this Italian monk and philosopher named Giordano Bruno. So in 1584, Bruno published a philosophical dialogue which presented, among other things, a cosmological system or model in which matter, or at least macroscopic pieces of matter, consisted of two main kinds of objects. Things he called Earths, plural. These were things kind of similar to our planet, but other planets would be Earths as well. And then suns, or things similar to our sun. But he thought all the stars, all those bright stars in the night sky were suns. They were things like our sun, but just farther away. This wasn't a popular idea from what I can read or what I can suss out from the history. It seems that a lot of people just thought that for that to be true, those stars would have to be ridiculously far away, very, very far away, much farther away than anybody was willing to take seriously. Of course, modern astronomers have just accepted that's true. They are really, really, really far away, and we're okay with that. But at the time, that was maybe a bridge too far. As a side note, Bruno's, career did not end particularly well. In 1600, he was accused of heresy by the Catholic Church, and he was burned alive at the stake, naked, after having his tongue cut out of his mouth. Oof. So, rough way to go. Sorry about that, Bruno. I guess it was a hard time for philosophers who weren't willing to toe the official line of the doctrinal church. You know, it was a rough time to be a free thinking, you know, cosmology minded Italian monk, I guess.
Yeah, it's interesting, the power of ideas. Was there any reason that he had to believe that the stars in the sky were like our sun, or was it just like a really good intuition?
You know, he wrote very briefly about it. There are only like isolated sentences or maybe paragraphs in that treatise about this. But like, he realized that objects of a fixed, what we now call luminosity, appear to be less bright if you move them farther away. So, you know, I think he just imagined what would it be like if the sun were, you know, much, much farther away, and in something like this, the stars began to look right.
Right.
He also, like, you know, he bought into the idea that the reason all the stars move in unison in the sky is because the Earth's rotating, not because all the, like, the celestial spheres are rotating or something. So he had a, you know, relatively progressive or modern view of those things at the time.
Good for him in 1584.
1584.
Even though it didn't do him any good in his life, it seems, but...
He earned a place in the pantheon of great thinkers.
He earned a place something. On our podcast.
Yeah, that's right.
Something to say.
Okay, so let's start talking about the sun itself. So in most ways, most respects, the sun is a fairly typical star, okay? It's basically a big ball of gas. Well, actually, that's just what people say. It's not really gas, it's plasma, okay? So when you heat up a gas, all the electrons break off the nuclei, and you're left with what we call a plasma of protons, electrons, and other kinds of nuclei. It's kind of like a gas, but without the electrons being stuck to the nuclei. So that's what the sun is made of. It's mostly made of hydrogen and helium. It's by mass, it's about 73% hydrogen and 25% helium. The little smattering of stuff that's not hydrogen or helium is stuff like oxygen, carbon, neon, and iron, but mostly hydrogen and helium. I said before that it's kind of a typical star, but it's actually a little bit bigger than average. Its mass is about 2 × 10⁻30 kilograms, which makes it a little more than 300,000 times as massive as the Earth. So, you know, a lot of Earth masses kind of all glued together in one big ball of plasma. And at this mass, it puts the sun in the top 5th percentile of all stars by mass. So if you had 100 stars, you know, the sun would be like the 5th most massive or something like that.
Actually, I didn't realize that it was so big.
Yeah, everybody says it's like an average star, but It's not really true. It's closer to being an average star of the stars we see when we look at the sky, but the smallest stars are the faintest and hardest to see. So you tend to see the bigger stars. So that's part of the story. Most of the stars in our universe are actually red dwarfs, which are smaller stars. So to give you a kind of a point of context, being in the top 5th percentile in mass for the sun is kind of like being, in terms of height, being like 6'2" if you're a man, or 5'9" if you're a woman. Like, you're definitely taller than average. You know, a lot of rooms you're the tallest person in, but, you know, you're not, you know, not super exceptional, you know, just a little bit bigger than normal.
You're like both bolstering and humbling the 60 people out there.
Sure. Yeah. I mean, you equate yourself with the sun. That's pretty good, right? So the radius of the sun, it's pretty much just a sphere, and its radius is about 700,000 kilometers. Which is a little more than 100 times the radius of the Earth, which means you can fit more than 1 million Earths inside the volume of the sun, for context. So it's pretty hard to imagine something this big, but it's really gigantic by the standards of planets, especially our own planet. On the surface of the sun, the temperature is about 5,800 degrees. I'm going to use Kelvin units, but it turns out it doesn't really matter what kind of unit you're using here. If it were Celsius, it'd be about the same.
Right, you just add 200 or whatever. So
yeah.
Not a big difference.
When the numbers get this big, they're about the same, yeah. And it's the temperature of its surface that sets its color, the kind of yellowish color we see when we look at the sun. Colder stars, stars with a lower surface temperature, tend to be redder. Hotter stars tend to be bluish or whitish in color. So you can kind of just measure the temperature of a star by casually looking at its color. As you go deeper beneath the surface of the sun, the temperature goes up and up and up. And this increases all the way into the core, where the temperature of the core of the sun is like almost 16 million degrees. So like dramatically hotter in the core. And that's an important feature because it's that high temperature that allows nuclear fusion to be taking place in the core of the sun. That's kind of the defining feature of a star. In fact, I would say that if you have an object and you want to say, well, is this thing a planet or is this thing a star? The answer to that question is, well, is nuclear fusion going on a lot in its core? And if the answer is yes, you've got a star. If the answer is no, I think you've got something that I might be inclined to call a planet.
So you're saying that, maybe a giant gas planet might have a little bit of nuclear fusion, but if it's not happening in a great quantity and producing a lot of energy, then it's not a star. But that maybe there's more of a spectrum between planets and stars than we normally think of.
I think that's right. So if I took something like Jupiter, which is the largest planet, that thing's made mostly of hydrogen and helium. It's a gas, but if you heated it up, it would start to be a plasma like a star. If you started to make Jupiter like double this mass, triple this mass, increase its mass more and more and more, eventually its core would get hot enough that you'd start to have a little bit of fusion going on. Stars in that kind of category, or in kind of planet star boundary objects like this, are called brown dwarfs. And if you made their mass even bigger, you'd become a more full-fledged star, what we call a red dwarf, and then eventually the sort of star that our sun is. So the kind of fusion that is mostly going on in the core of the sun is something we call the proton-proton chain. So this is like a multi-step process. So we take two protons. Through fusion, they turn into a deuterium nucleus, which is like a proton and a neutron bound together. And in that process, they release some other particles. And then those deuterium nuclei fuse together to make helium-3, and then pairs of helium-3 fuse together to make helium-4.
So what does it mean when we say things like helium-3 or helium-4 here? So while the element helium is defined by having two protons in its nucleus, it's possible for those two protons to be bounded to one neutron, which will form helium-3, or two neutrons, which would be helium-4. We call these different isotopes of helium, and the number after the name tells us how many total protons and neutrons there are in the atom.
So when this whole chain is done, you've taken 4 protons, converted them into a helium nucleus, and produced a pair of photons, a pair of positrons, which are kind of like the antimatter version of electrons, and a pair of neutrinos. So in this whole process, the total mass of the particles involved goes down by just a little bit. And that means, according to Einstein's most famous equation, E equals mc squared, that change in mass corresponds to a release in energy. So every time this happens, a little bit of energy gets released. And in this case, that energy is in the form of those photons and neutrinos, which kind of move away at high speeds, carrying away energy with them. So this sort of proton-proton chain fusion is going on a lot in the core of the sun. It happens, about 4 times 10 to the 38 protons are fused together into helium in every second of every day. So a truly mind-boggling number of reactions are going on all the time. And if you look at this in terms of total amount of mass, it corresponds to about 600 million tons of hydrogen, or protons, if you will, that are being transformed into helium every second. Not all of this mass is lost. Most of the mass start out in the protons, wind up in mass in helium, but about 0.7% of the mass is actually lost for real. And that means that the sun is losing mass at a rate of about 4 million tons each second.
Wow.
It sounds like a lot of mass, but the sun, remember, is really big. So it's actually a really slow process. But the sun is getting smaller, or it's smaller, lower mass and actually smaller too.
Whoa, that's a lot of mass.
It is. So a lot of that energy goes into these particles called neutrinos, and they don't do much to heat our planet. They just kind of fly off in all directions and disappear. But the photons are the other part of the energy. they actually have a hard time getting out of the sun. Like the sun is a big dense ball of material, right? So if I tried to shine a beam of light through some big dense ball of material like the Earth or something, it wouldn't go very far. But these photons kind of bounce around, hitting different things, doing this for a long, long time, but eventually reach the surface of the sun and get radiated as sunlight.
You may have heard before that light takes 8 minutes to travel to the Earth from the sun, but that's only part of the story. The trip takes 8 minutes once you leave the surface of the sun. But that process, from being created to reaching the surface, takes much, much longer than that. Something like tens of thousands or maybe even hundreds of thousands of years. So that's a whole lot of bouncing around inside the sun that those photons need to do before seeing the light of day, so to speak.
Yeah, so the first part of the trip is like long and arduous and slow and everything, and like, tens or hundreds of thousands of years, and then hits the surface and like, we're free, and they just go in a straight line, and if that straight line happens to go towards the Earth, it hits us and heats up our planet a little bit, maybe does some photosynthesis, all that sort of thing. So the total amount of energy we're talking about here is about 4 times 10 to the 26 watts. It just seems like a mind-bogglingly huge number, of course. You can also think about it in terms of like 90 or 100 billion megatons of equivalent of TNT per second. So it's just more energy than anything you or I can easily like wrap our heads around. Stars really produce a lot of energy. We've talked about the fusion part of this story now. So all this fusion is producing all these particles, and those photons are like pushing outward away from the core towards the rest of the sun. And that kind of wants to puff up the sun. It wants to push outward and wants to make the sun expand outward. But working against this is the force of gravity, which of course wants to pull the sun towards its center of mass. So there's kind of fusion pushing outward, gravity pushing inward, and these two things tend to balance, allowing the sun, or any star, but the sun in particular, to reach a state that we call hydrostatic equilibrium, where it's not getting any bigger and it's not getting any smaller. It reaches, at least on long time scales, approximately stable, static configurations. If the rate of fusion in the sun's core were to turn up for some reason, it were to increase, the sun would expand because the pressure would go up, the fusion pressure. But then as the sun got larger, it would cool overall, and that would cause the fusion rate to go down and would shrink. So you can see that there's kind of like a self-governing system here. It tends to drive, as long as you have plenty of fuel and the same kind of fuel in the core and stuff and nothing dramatic happens, the size of the sun will increase or decrease until the state of hydrostatic equilibrium is reached between gravity and nuclear fusion.
So it's a pretty stable equilibrium.
At least for now. I mean, the sun's been around for 4.6 billion years, and it's changed slowly over that time, but nothing dramatic has happened over that window of time as far as we know.
So far, we've talked a lot about what the sun is like today, but to understand how it came to be, let's go into the past.
Like all stars, the sun formed out of a giant cloud of gas. And basically, when you have one of these enormous clouds of gas, the densest parts of those clouds tend to collapse under the influence of gravity. And if those little parts of the collapsing cloud are dense enough or massive enough, they can form stars. These kind of star-forming clouds are usually really, really huge, and they don't just like make one star. So don't picture like a cloud that collapses and makes the sun. Picture a much, much larger cloud that produces a huge number of stars. That's more prototypical of the sort of stuff you find in our universe. These sorts of star-forming regions make for some of the most beautiful images in all of astronomy. I encourage our listeners to Google JWST or Hubble along with the phrase star-forming region or star-forming cloud or something like that. And you will get these beautiful images of just dramatic color and light with newly forming stars. It's really fantastic. So check that out. It's very worth it. So as these clouds, these small individual clouds or star-sized clouds collapse, they form things that we call a protostar. which, are starting to have some fusion in their core maybe, but mostly they're big, hot clouds of gas, and they don't collapse very well all the way yet because they're so hot from all the gravitational collapse and all the energy they got that way. But as they cool down, they compress through gravity into a smaller and smaller volume, and eventually they compress so much that fusion really can begin to take off in their core, and this sort of hydrostatic equilibrium can get established, and we can find ourselves with a sort of like a young version of the sun that can come out of this process. So when you have a star that's in this state of hydrostatic equilibrium, that's fusing hydrogen together to make helium, we call this sort of star a main sequence star. Okay, and this is kind of like a stable configuration. So you're taking all the hydrogen in your core, turning it into helium. This lasts a long time, depending on how big the star is, but it can last anywhere from, hundreds of billions of years to, hundreds of millions of years, depending on exactly how big a star you're talking about.
This is likely how our sun formed. And despite appearing to be in a pretty stable equilibrium, it has continued to change throughout its lifetime and will continue to change in the future.
So as time went on, the sun gradually began to change. The process of fusion that was going on in its core changed the kinds of elements that you could find in the sun. And that in turn began to change the rate at which fusion would take place. And when you change the rate of fusion, you can change the temperature, you can change the size of a star. Overall, we think the sun started out when it was young with about 24% of its mass being helium. Okay. This is only slightly less than the abundance of helium that we find in the overall sun today. Okay, so it hasn't changed very much. But if instead of looking at the sun as a whole, we just focus on its core, the part where the fusion is going on, there we find that the abundance of helium has changed quite a lot, increasing from this 24% number when it was young to about 60% today. So about 60% of the sun's core today by mass is made of helium. So it's a mostly helium core, even though it started out mostly being made of hydrogen.
So does that make it like a teenager or a young adult?
Yeah, I think it's roughly, you can think of it as midway through its life cycle.
Oh, okay, midlife.
Yeah. I mean, modern life expectancies, I think, this is a, middle-age sort of star. Yeah, right in the middle of its life cycle. As time goes on, this fraction of helium in the sun's core will only increase, okay? It's 60% now, but it will eventually go to 65 and 70% and all that stuff. And since it's hydrogen nuclei, the protons in the core that we're burning through fusion to make the fuel that makes the sun do its thing, this fuel is getting kind of displaced by all this helium. Like a smaller and smaller fraction of the core is made up of usable nuclear fuel, because it's used up all its fuel over the last 4.6 billion years or so.
Less fuel left means less fusion pressure pushing the star outward. As a result, gravity pulls the star in more, which causes it to heat up again and find a new equilibrium.
So this change gradually causes the core of the sun to compress and heat up. So it's actually getting hotter because it's running out of fuel. It's a little counterintuitive, but basically, it's pushing out less, so the core squeezes together, causing it to actually get a little hotter. So it's kind of this weird cycle, okay? As the core compresses and heats, this in turn causes the overall volume of the sun, not the core, but the whole sun itself, to become bigger and to heat up. So the surface temperature of the sun actually is going up slowly over time. Not very quick, but slowly. So like today, for example, the radius of the sun is something like 15% bigger than when the sun was young. So it's kind of puffed up a little. It's not dramatic, but 15% is not nothing, right? And the surface of the sun is about 150 degrees hotter today than when it was young. So again, we're talking about like 5,800 degrees. So 150 degrees isn't a huge change, but it is a little bit hotter than it used to be. So when you take into account the bigger overall size or radius of the sun and the hotter temperature of its surface, these things together tell you that the sun is brighter today than it was in the past, and it will continue to get brighter into the future. It's probably about 50% brighter today than when it was young. So like substantially brighter. All these factors together make the sun quite a bit brighter than it used to be. In the very, very distant future, this is going to be a problem for those of us on Earth. After another couple of billion years, the sun will be so bright that things like liquid water will like evaporate on the Earth, and we will have, unless we do something about it or have some technology that saves us or whatever, we will experience a dramatic final mass extinction as the sun gets brighter and hotter and bigger.
Before anyone gets up in arms about this, remember that this is happening really slowly for human timescales. Like, we're talking about a 1% change every 100 million years or so. So there are certainly more pressing issues to worry about.
So this is going to go on for a long time. Like we said before, we're kind of in a middle-age state of the sun's life. It's been around for about 4.6 billion years. And in another roughly 5 billion or so years, we're going to have the hydrogen in the sun's core pretty much wiped out. So the thing that we're using for nuclear fuel now is going to be exhausted. I mean, there will still be traces of it, but not enough to keep the sun going along its normal trajectory. It will take it off what we call the main sequence, and the sun will start to do, some more volatile and violent things. So when this fusion kind of shuts down, the core is going to contract because there's no pressure pushing out anymore. That's going to cause the star to become hotter and then expand. And I mean really expand. It's going to expand a ton. So we were talking before about like the radius growing by 15%. That is nothing compared to what's going to go on at this kind of late stage of the sun's evolution. It's going to grow so much that it's going to completely swallow up Mercury and maybe even Venus. It's not completely clear. But it's going to grow to about 0.75 astronomical units. So the radius of the sun will extend about 3/4 of the way to the Earth. Okay, so a lot bigger than it is now, dramatically bigger. In this state, which will last for something like 1 billion additional years, the sun isn't a main sequence star. Instead, it's this thing we call a red giant star. I think the name is pretty self-explanatory. It's red because, it's a little, surface temperature is a little colder and it's than it was in its current state. And it's a giant just because it's gargantuanly larger than a normal main sequence star. In this phase, this billion-year phase of its evolution, the sun will be about 1,000 times brighter than it is today. So dramatically brighter. You can imagine that this would be really bad for the Earth. 1,000 times as much sunlight as we currently get will fry everything pretty much instantly. This is not a habitable solar system at that point. Also in this phase, the sun is going to expel some of its matter. Basically, it's going to be so volatile that it's going to throw off a bunch of its matter. It's going to lose about 1/3 of its total mass in this stage of evolution. So the red giant phase that we're talking about now for our sun will end when the helium in its core, not the hydrogen, but the helium now ignites and starts undergoing fusion itself. So before we were talking about this proton-proton train where you're taking protons and making them into helium, but now we've got a core that's all made of helium. The helium itself, if it gets hot enough, and it does in this phase, it will start undergoing fusion in its own right. We call this transition the helium flash, and it kind of turns on pretty suddenly, at least by the timescales of stellar evolution. So in a matter of like minutes, roughly, something like 2 to 3% of the sun's total mass will be converted from helium into carbon through a process we call the triple alpha process. 2 to 3% maybe doesn't sound like a lot, but this is happening almost instantly. Usually, if you want to talk about something happening in a star, you have to talk about hundreds of millions or billions of years. You don't talk about minutes or seconds. But once you breach this threshold and helium fusion can start, it really, it's a pretty dramatic and sudden transition. As this all ends, the sun will slowly start to shrink and cool, gradually burning up the remaining helium that's in its core. And this is going to take something like 100 million years. So pretty short by stellar evolution, but nothing, nearly as sudden as the helium flash or the helium ignition that really triggers this phase. When the helium in the sun's core runs out, it will kind of do this expansion giant thing all over again, kind of like it did when it ran out of hydrogen in its core and started its trajectory into the red giant phase. But this second time, it will play out even faster, and the sun will become even larger and brighter this time around. It will definitely engulf Venus this time if Venus wasn't engulfed the first time, and it might even engulf the Earth. We're not really sure, but something right around there. The other outer planets will keep in their orbits, we think, around the sun, but the sun will be much, much brighter, and those planets will be much, much hotter than they currently are. During this stage, the sun will lose even more of its mass, and will be even brighter than that 1,000 times brighter than the current sun we mentioned before. Astronomers are fond of red giants because they're pretty useful. They're so bright that you can see them at really great distances. So it's actually pretty useful. Like I know some astronomers in my department who are using red giant stars to try to measure how fast the universe is expanding. And the main reason that they're useful is just because they're so bright and you can see them from great, great distances with kind of attainable telescopes. If you had an infinitely large telescope, we might not care. But with our real world telescopes that can only see things with a certain degree of brightness, red giants are a really great target. When all this is done, the sun will have about half as much mass as it does today, and most of that mass will consist of things like carbon and maybe some oxygen. So by this point, it's completely transformed from that ball of hydrogen helium into a completely different kind of ball made mostly of carbon, oxygen, and things like this. At this stage, there will really be no nuclear fuel left for the sun to burn, and there will be no fusion pressure to work against the force of gravity. So you might think that gravity just wins and it would squeeze this thing down into a point, maybe making a black hole or something, but there are other things that can prevent that from happening in the case of a star like the sun. In particular, as you squeeze this carbon and oxygen material down, you reach a point where there's something called quantum degeneracy pressure pushes back against gravity and leads to a stable state.
Quantum degeneracy pressure sounds complicated, but it comes down to something that you may have heard of called the Pauli exclusion principle. This principle from quantum mechanics tells us that certain kinds of particles, like electrons, cannot inhabit the same state as one another. This is the reason that we describe atoms as having different orbitals, where as electrons are added to an atom, they have to take on a new energy level. And it's also why it becomes harder to squeeze matter into a smaller and smaller region after the death of a star.
Since there are electrons in this state of the sun's evolution, there are only so many states you can put those electrons in, and that means you can only pack those electrons into so small of a volume. It's a pretty small volume, okay? So that half of a solar mass worth of material, the carbon and oxygen, will get squeezed down in this phase into a volume roughly the size of the Earth. So remember that the sun is 1 million times or more than 1 million times the size of the Earth by volume. So it's going to squeeze the whole sun essentially into something a million times smaller by volume, something roughly the size of the Earth. We call this state a white dwarf. This carbon and oxygen is going to be really weird. It's going to be super, super dense, much denser than anything, we are familiar with in our day-to-day lives. People like to say that this carbon is going to kind of be like a giant ultra dense diamond. And that's probably the best analogy we have to work with. But definitely not like the kind of diamond that you might have in a wedding ring or something. This is, much, much denser and frankly, much, much more exotic. In this state, there's no fusion going on, so there's like no new sources of energy. They just basically start out with all the energy they had from their collapse and all the gravitational potential energy that went into it, and then they slowly cool. So when a new white dwarf like this forms, it might have a surface temperature of something like 100,000 degrees, so way hotter than a normal star. But they're also really small, so they're actually not all that bright. I mean, brand new white dwarfs are pretty bright, but they get pretty faint and pretty dim relatively quickly. So after about a billion years or so, one of these ultra-hot white dwarfs will cool down to maybe 10,000 degrees. And then after another 10 billion years, that sort of star will cool down to a few thousand degrees. And this just continues on indefinitely. You know, if you found a white dwarf and waited a trillion years or something, it would basically cool down to the sort of, like almost planet-like temperatures. And we call these sorts of hypothetical states that, don't exist because our universe hasn't been around long enough to create any. But if they were to exist, we'd call them a black dwarf, something that had cooled to a point where they're not even radiating light. And they just cool forever, I think. There's no point where they reach a stable state. They just keep cooling and becoming fainter and fainter and fainter.
Stellar grave.
All right, so that is the past, present, and future of our sun. In the next episode, we're going to take this a little farther and talk about stars that aren't like our sun, other kinds of stars. Some of those will be different kinds of main sequence stars, like we talked about a little bit today. But those will look different depending on if they're bigger or smaller than the sun. And we'll also talk about other kinds of non-main sequence stars, including really exotic things like neutron stars and black holes.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.